All right, cool. So today we are talking about momentum. Momentum is an interesting one. I feel like, again, it's one of those things that you have probably heard that word used often in your life, but it's usually not from a scientific standpoint. Right? Like a lot of times, oh, if a sports team has a lot of momentum, that means they're doing really well, they're going to be hard to stop, things like that. That's not really a physics way of looking at the concept. But it will be a good analogy for us to use in a little bit. For now, let's talk about momentum from a physics standpoint. Isaac Newton was the guy that came up with momentum. It kind of was one of the very first things he came up with when he was working out all of his, laws of motion and his equations and stuff like that. So when Newton came up with the concept of momentum, he defined it as an object's quantity of motion. An object's quantity of motion. That's a weird definition, right? How do you quantify motion? Well, to do that, let's go back to that sports analogy. Let's think about that team that's hard to stop, right? They're doing well, they're hard to stop. Let's use that as our analogy. Let's say that to figure out what momentum is, we'll figure out what makes an object hard to stop. Okay, well, let's imagine that I have two people standing here playing catch. And in this guy's hand, he's got a baseball. Let me see if I can draw a baseball in there. Oh, beautiful. So he's got a baseball, and he's going to throw it at our other guy over there. Okay? If he takes that baseball, throws it rather lightly, kind of at a slower velocity, then the other guy who's catching the ball over here is going to catch it pretty easily, right? It's going to be pretty easy to stop that baseball because it's moving at a lower velocity. Okay, so what if we threw it at a higher velocity? Throw it faster. Well, your natural inclination would be, yeah, that's going to be harder to stop. The object's moving faster, so it's going to be harder to stop. So let's write that off to the side. I think velocity is going to have a factor in figuring out the amount of momentum. How fast the object moving is going to help us figure out how hard it is to stop. Okay, but what if, rather than giving our pal a baseball over here, what if he threw something slowly, but it was a very heavy object? Let's say he has a bowling ball instead. Well, even if he threw that slowly, it's going to be hard to stop, right? It's going to be hard to catch a bowling ball. You don't really catch bowling balls very often. Why is it harder to stop? Because of the mass it has. I'm going to write that down too. These two properties, mass and velocity, are going to be our building blocks for momentum, okay? So check it out. Our equation for momentum looks like this. Momentum is represented by a lowercase p, all right? Lowercase p is the variable which represents momentum, and to calculate it, very simple. It's mass times velocity. That's it. There you go. That is the momentum equation. Now, let's take a second, talk about units here. We know mass has units of kilograms, and velocity has units of meters per second. Therefore, our units for momentum are going to be kilogram meters per second. Kilogram meters per second. Okay. Normally, a lot of times we have fancy names for these kind of long-winded units. In this case, we don't. Unfortunately, when it comes to momentum, you got kilogram meters per second, and that's it. All right? Cool. Now, what I want to do next is I want to compare some student data from the lab we did the other day. In that lab, we had two carts sitting on a track. One cart was sat stationary, and the other cart was pushed towards the stationary cart. Okay? Here's what I want to do. I want to compare the momentum before the collision and after the collision. Okay? So check this out. Before the collision, this group of students got a velocity of 0.75 meters per second. And after the collision, they got a velocity of about 0.3668 meters per second. Okay. Well, we know that the mass of these carts is about 0.25 kilograms. So let's look at the momentum. It's going to be mass times velocity. So that's going to be 0.25 times 0.75. Plug that into my calculator. Give me a second here. So I'm getting momentum equals 0.1875 kilogram meters per second. All right. Now we're going to do the same thing over on the right side after the collision. Here's the difference though. After the collision, the two objects hit and stick together, essentially becoming one single object. So rather than saying it as a mass of 0.25 kilograms, I'm going to double that mass, say it's 0.5 kilograms. Okay, well, let's find the momentum from there. Mass times velocity, so 0.5 times 0.368. Plug that into our calculators. 368. I got, let me write it down here actually, 0.184 kilogram meters per second. Okay, what does this show us? Well, it's not perfect in this case. No situation in real life is going to be perfect, but look at this. 0.184, 0.187. What does this tell us? This tells us that the momentum was the same before and after the collision. This brings us to a big idea about momentum, and that is the concept of the conservation of momentum. And what does that tell us? Well, it tells us that the momentum in a system, sorry, I guess I should say the total momentum in a system, just to be very clear. The total momentum in a system will be conserved during collisions. However, there is one rule that goes along with that. And it's very reminiscent of our rule with energy, right? Think back to our conservation of energy unit. When was energy conserved? As long as there were no outside forces, right? Same thing here. No outside forces. Must be a closed system in order for this to work. All right, so as long as there are no outside forces in the system, we are going to have momentum conserved in that whole system. What I want to do is I'm going to take conservation of momentum as a concept, and essentially I'm going to turn this sentence into a mathematics sentence, an equation that we can use to help us solve for certain scenarios. Here's what it's going to look like. So the momentum of object A, which is its mass and velocity, initially, plus the momentum of object B, mass times velocity initial, equals the momentum of object A final plus the momentum of object B final. All right? So all I've done is I've taken the sentence up at the top here and turn it into an equation. I'm just saying that all the momentum in the system added together equals all the momentum in the system added together. So this is going to be before the collision. This is going to be after the collision. All right. So there you go. That is our conservation of momentum equation, and it's going to help us out quite a bit. So let's use it in a practice problem. So let's imagine we've got two rail cars, two big trains. And kind of like our lab, what we're going to do is we're going to have one of those rail cars be stationary. So this one we'll say is stationary. And the other one will be traveling at a velocity of 24 meters per second. And you know what? Let's make things a little bit more difficult. Let's give them different amounts of masses. Let's say that the mass of this one is 10,000 kilograms, and the mass of this one is 8,000 kilograms. All right? So the 10,000 kilogram is going to hit the stationary 8,000 kilogram rail car. Our job here, I want to find the final velocity of these two rail cars. By the way, when they hit, they're going to stick together. All right? So we're going to pull out our conservation of momentum equation here. It's going to look like this. Sweet. All right. So we got to start filling in information with what we know. Well, mass of A is 10,000, and it's moving at a velocity of 24 meters per second. Okay. Mass of B is 8,000, but it is fully stationary, so that's times 0. On the other side, I'm going to switch things up just a little bit. Rather than having two different amounts of momentum, well, the two objects collide and stick together. So again, we're going to kind of think of them as one single object. So what I'm going to do on the other side is I'm going to add their masses together, 18,000, and because they're stuck together, they're going to be moving at the same velocity, right? So that's just going to be our final answer there. All right. So let's start plugging stuff into a calculator. So we got 10,000 times 24. So over on the left-hand side, the total momentum in the system before the collision is about 240,000 kilogram meters per second, right? And that all equals 18,000 times the final velocity. Okay, so to solve for final velocity, we divide by 18,000. We come up with the answer of 13.3 meters per second. So now we know how fast those carts are going to move once they collide with each other. All right, let's try a different, slightly more difficult issue. It's a more difficult problem here. So imagine that we have two pool balls. There's one, there's the other. Let's give them some colors. This one will be the green striped one. Beautiful. And the other one, let's make it the red striped one. Ah, wonderful. All right. So in this case, let's say that for some reason those billiard balls have different masses. So the red one over here has a mass of 4 kilograms, and the green one here has a mass of 2 kilograms. All right. So what's going to happen is green ball is stationary at the start. Meanwhile, red ball is moving at 5 meters per second to the right. Okay. However, they're going to collide, but they're not going to stick together. And we know that after the collision, so let's redraw what it's going to look like after the collision. So they're going to collide. They're not going to stick together. That and then green. Okay. we know that the green ball is going to move off with a final velocity of 6.67 meters per second. And I want to find what is the velocity of the red ball after the collision. All right, so definitely a bit more complicated here. Let's set up our conservation of momentum equation one more time. Okay, we can start plugging in numbers here. We know the mass of ball A, or the red ball in this case, is 4, and it's moving at a velocity of 5. The green one has a mass of 2 and is not moving. Okay, and then on the other side, I can't combine these two terms, right? I can't add their masses because they don't stick together. So we know that red ball has a mass of 4, and we're trying to solve for its final velocity. And green ball has a mass of 2, and we know it's moving at 6.67 meters per second after the collision. And now we can start solving stuff. So 4 times 5 is going to be 20, plus 0, anything times 0 is 0. And we have 4 VF plus 2 times 6.67. It's going to be about 13.34. Okay? So we'll subtract 13.34 from 20, and we'll get 6.66. 6.66 equals 4 VF. Divide both sides by 4. I got a final velocity of 1.665 meters per second. Okay, cool. All right. That was another scenario. Now what I want to do is I want to investigate kind of a weird thing, something you might feel is unrelated. I want to look at the amount of energy in the system before and after. All right, so check this out. New page. Looking at the energy before and after. Let me split the top here. Here's going to be before. Here's after. Now in both cases, the only type of energy we're looking at is kinetic energy, right? So we'll find the kinetic energy of the red ball, kinetic energy of the green ball, and then we'll add those two, and that'll get us the total energy. All right, so we're going to compare the total energy here. So kinetic energy for the red ball is going to be 1/2, mass is 4, velocity was 5 squared. And then for the green ball, we have 2, velocity was 0 squared. Okay, so plug that into my calculator. 5 squared is 25 times 4 is 100 divided by 2. So our total amount of energy in the system is 50 joules before the collision. But what about after? Okay, well, we have the kinetic energy of the red ball. We know the red ball still has a mass of 4 and a velocity of 1.665 now. So let's plug that into a calculator, see what we get. K times 0.5. All right, so there I got 5.53. And the green ball is going to be 1/2 of 2 times 6.67 squared times, that gets me about 44.48. Okay, so our total energy over here is going to be 44.48 plus 5.53. I got, surprisingly enough, about 50 joules again. So what does this tell us? For some reason, not only is momentum being conserved, but in this case, energy is being conserved. And this brings us to a distinction between two different types of collisions we're going to deal with in this class. The two different types of collisions we deal with in this class are elastic collisions and inelastic collisions. Okay? At a very basic level, one way you could think about this is that elastic collisions, the objects bounce off each other, And inelastic collisions, objects stick together. But that's a little too basic for us here in AP. We got to take it one step more difficult, I guess. So actually, our real definition for an elastic collision is when energy is conserved in the collision. When energy is conserved in collision. And inelastic is when energy is not conserved. Okay? So, if you're ever asked to figure out, is this collision elastic or inelastic? Yes, you can start by saying, oh, well, here they stick together, so I kind of think it's inelastic. Or, oh, in this one, they bounce off each other, so I kind of think it's elastic. But the only way to know for sure, is to check the amount of energy in the system. You have to check the amount of energy in the system to figure out whether it's inelastic or elastic. Otherwise, it's just a guess. All right? Actually, one helpful way I think of it, just to help you keep it in your brain, elastic, energy is conserved. They both start with an E, so that might help keep that in your brain, a little reminder there. And yeah, there you go. That wraps up all we need to know about momentum and conservation of momentum here. Hopefully this was helpful to you. All right, see ya.